So here we can see that we're just driving, we have 51 frames. So this is basically just our trip that we're running through. Now we can see that we're estimating all the poses. We get around like 6 poses estimated per second, and when the program here is done, it will open up an HTML file and show the results. Hey guys, and welcome to a new video in this computer vision tutorial. In this video here, we're going to talk about visual odometry, which is stereo camera. So in the last video, we did visual odometry with a monocular camera. We talked about like what is the pipeline, what is visual odometry, and also at the end of that video, we set it up in OpenCV with Python. In this video here, we're going to focus on stereo camera. So we're just going to convert it from monocular camera to a stereo camera where we're using 2 images instead of only 1 image. So we'll also get depth information in our images. But first of all, remember to join the Discord server. I'll link to it down in the description here. You can join the channel, shadows about computer vision, deep learning, AI, and so on. You can always become a member of the channel if you want to support the channel with a small monthly fee. Everything will go to create more and better quality content here on the channel. Also, if you're a member of the channel, I can help you out and give some guidance in your own projects where you have some problems if you're a member of the channel. So thank you guys. So first of all here, we're going to have a short summary of what is visual odometry, how can we use it, and how can we actually set it up, and what is the pipeline and idea behind visual odometry. If you want to know more details about visual odometry, make sure to check out the last video I did with visual odometry with a monocular camera. So in this video here, we're just going to do short summaries, and then we're going to jump into the code, implement it with stereo vision, with stereo images, and then we're going to see the results at the end of this video. But first of all here, we're going to talk about like what is visual odometry. So visual odometry is about estimating the pose of a camera by examining the changes that motion includes in the images. So basically here we just have a number of images that we go through frame by frame, and then when we're moving around between those frames, we can actually like spot or like we can detect some different kind of features from frame to frame. Then we can match those features together, see how the motion actually changes in our images. So we're actually just tracking down features, seeing how are they actually moving from frame to frame, and then we can estimate the pose of our camera and thereby doing visual odometry, but only using a camera. So basically here we're just looking at different features in the frames and tracking them, as we can see as an example down at the bottom image here. So we just have an image view here of an environment that we're driving in, and then we're just detecting a number of features here in our image. So all these green dots here are features that we are actually like detecting, and then we can track those exact same features from frame to frame, and then we can estimate the pose of our camera to get visual odometry. So here are some of the results that we can get from visual odometry. We can see here the benchmark from the OR Visual SLAM paper. So here we can see the ground truth in the red, and also over here in the black. So we have the ground truth in the black, and the red is the estimated pose of the camera when they're doing visual odometry. We can see an example here to the left where they're driving around in the environment. We can see some of the black dots, which is actually like the points projected out from the images to the real world, and then we can see the path here that the car is driving with the green line. So this is actually like really nice result that we can get from using only visual odometry. So we can use it for like different kind of things. So here are some of the applications that we can use it for example, like self-driving cars and also robots. So we could have a robot where we just attach a camera on top of the robot. It can drive around the environment in warehouses or some other places, and then we can actually use visual odometry to track where's the robot moving around, how is the environment. We can combine it with SLAM and so on for mapping environments, and also localizing a robot or some different kind of objects in environments as well. It can also be used for like space exploration, stuff like that. If we haven't been on Mars, we don't know the environment on Mars, we can just have cameras driving around, use visual odometry to map the environment and also localize what is going around, like what is going on around the robot. So now we're going to talk about the difference between visual odometry and visual SLAM. So the basic idea here is actually just before we're not closing any loops in visual odometry, we're just driving around estimating the pose. But when we're talking about visual SLAM, which is simultaneously localizing and mapping of the environment, then we're actually like closing the loop. So we need some kind of way to detect loops in our path that we're driving on, and then after we have closed the loop, we can actually like do some global optimization, so we can refine all the poses that we've been through and estimate it throughout the path or the trajectory that we have driven with our robot or a car in this example. So here we can do loop detection with some different kind of things. We can, for example, if we're re-observing a landmark after not seeing it for a long time, then we can say that if we see a couple of different kind of landmarks, we are now at the same place where we have been before, and then we can say that we have now detected a loop. We can go back, do global optimization, and refine all the poses back in that loop that we have driven. We can also, if we're coming back to previously seen or like mapped areas, we get some different kind of like matches with our features that we have seen before. It is also a loop. and we can just look at the similarities between the current frame and all the past frames that we've been through before we have seen a loop. And then we can actually just compute here with global or like local image descriptors. So actually we can use something called visual bag of words and stuff like that we're going to cover in another video. So make sure to subscribe to this channel. Also hit the bell notification so you get notifications when I upload new videos here on the channel, because we're going to go do some really nice projects with Visual Odometry, SLAM. We're going to do like visual bag of words, how we can store information from our images, matches to previous frames and so on. So we can do localization, tracking, mapping, and so on. So the last thing here is just the pipeline before we're going to jump into the code. So here, Visual Odometry, it actually just computes the camera path incrementally. So we just go pose after pose or frame after frame. Now here at the bottom, we can just see two images here. So one frame is the first frame and the second frame is the second frame. And then we're actually just detecting the same features. We track those features from frame to frame, and then we can estimate the pose as we can see in the flowchart over here to the right. The bottom here is actually just local optimization. So we're just taking in an image sequence. We're doing feature detection, then we're matching the features that we're detecting. Then we can estimate our pose, and then we can actually then optimize it locally when we're just talking about visual odometry. So when we're talking about SLAM, we can also do some global optimization when we're detecting loops. So now we're going to jump straight into Visual Studio Code here. We're going to go through the code for setting up visual odometry for a stereo camera. In the previous videos, again, we did it from monocular camera. We're going to take the same code as a baseline, and then we're just going to add another image, do some other different kind of like algorithms, how to detect features in the images that can speed up the process a bit, because now we're actually like doing all the techniques and all the processing and running the algorithms on two images instead of only one image with the monocular camera. First of all, here we're going to import the different kind of modules that we need. So we need NumPy, OpenCV, and we're also going to use this lib here for visualization. So this is basically just for plotting the ground truth and also the estimated pose at the end, and also to play the trip here or like run through all the frames and images that we have in our KITTI sequence. So we're going to have two sequences here at the end of the program where we're going to run through the sequences, and then we can just see the results, how are we estimating the pose, what is the ground truth, and then we can actually like calculate the error and also see the error, how large is it, how good are we actually like to track our car or a robot going around in the environment. So over here to the left, this is just our data structure or like our folder set up here. So we have the data, we have the KITTI sequence 1, KITTI sequence 2, then we have a lib module here just for plotting and visualization. And then if we're going to one of the sequences here, we just have the left images and the right images in one folder. We can just go in here and see a couple of examples here. So we can basically just see here a car driving in a straight line. We both have the left and the right images. We also have the calibration camera parameters of our camera. And then we also have the ground truth poses here that we can then calculate the error from our estimated poses. So we can also get an error and see how far are we from the ground truth. So we're both going to have a sequence 1 and a sequence 2. And if we just go in here, this is just another environment. So we can test some different kind of environments and also some different kind of path and trajectories with these two sequences. So again, we're just importing the modules. We're also importing here from SciPy Optimize, because we're going to use least square to do some optimization later on and also solve for our poses. Then we can just go down here, create our class here, use the baseline as we did in the monocular derivation camera. So I won't really go into more details from that video. So basically we're using that video as a baseline. You can go check that out if you want to know more details about like how to set up this class or different kind of functions and so on doing. But first of all here, again, we need to load in both the left images and also the right images. We're just going to have a load image function. Again, all these things here are described in the previous video, so make sure you check that out. We're just going to load the poses here, the ground truth poses, load the images and also the camera parameters, both for the left and the right camera. Then we're going to set up a disparity map creator. So basically here, we're going to create a stereo like setup here. So we have two images. We just want to calculate the disparities because we have rectified images with our stereo camera. So we're going to create a stereo SGBM create here. So basically this is a function that we called from OpenCV. So this will create a disparity map from the two images that we pass in to it. And then we can actually use that disparity map to find depth in our image when we're actually just comparing the features that we find in the left image to the features that we find in the right image. Then we can match those two images, or like we can match those two features, and then we can triangulate those, get a really good 3D point in our environment. So we actually get the real world coordinates when we're actually doing this stereo vision, where we get our disparities and also our depth when we know our camera parameters. So we're just going to create this one here. Again, we also have videos about depth maps here on the channel. Then we're just going to set up our disparities. Our disparities will just be self.disparity.compute. So basically this is just a function to compute our disparity map from our left images and also for the right images. Then we just set it up as floating point 32 values. We're going to divide it by 16 because we need to do that. It needs to be divisible by 16. The OpenCV documentation says that. So we're just going to set that up. And then we're also going to create our feature detector here in this example. And in this video here, we're going to use the fast feature detector. So in the last video, we used the orb features to actually track our features from the one frame to the other and also detect the features. But in this video here, just to speed up the process a bit, we're going to use the fast feature detector. It is basically just a bit more, it is actually a bit more just focused on detecting corners than actually like really good features in the images, but it can still be used for tracking features and also detecting them and tracking them from frame to frame. We're going to set up our parameters here, again, that we're going to use later on. So this is basically just a dictionary with these parameters that we set up, so we can actually like display the matches that we find in our images. Then we have a load calibration here. Again, we won't go into details. We're just loading our calibration file. We're loading the pose file, and then also loading the images. So basically here, we're just going to have the path for our images. We're just going to have a for loop running through all those paths, and then we're just reading them in with OpenCV, and then we read them in as grayscale images. And then at the end of the function, we just return our image. We also have a function here for forming transformation. So we can just pass in our rotation matrix and also our translation matrix, and then it will return a transformation matrix that we can then use to do operations on. So basically the transformation matrix is our estimated pose at the end of the program here. We're just going to minimize those here so we get a bit better overview. So these are all the different kind of like default functions that we have just to do some different kind of operations. So now we can actually go down here, create a function for reprojecting our residuals. We can read here what the function here actually does, but we will go down to the bottom here so we can actually see what are we calling, like what different kind of functions are we calling. We're just going to take the pipeline, the flowchart that we had in the slides, and then we're just going to go through that and do all the different kind of functions. So if we go down to the main function, to start with, we're just going down here. We have our data directory. We can just specify the KITTI sequence 1. We can also specify 2 here, and then it will run on the second sequence that I showed you in the start. Then we're going to create an object here with our Visual Odometry class with our data directory, and then we can just return this object with our Visual Odometry. Then we can play the trip if we want to. If you want to see like what is the trip, we just go through it frame by frame. We're just going to play the trip with our left images and our right images. Then we have a function, or like we have a for loop here running, just getting the estimated path and also the ground truth path. And then when we have those two paths, we can actually compare them and we can take the difference between those two because those will be our errors. And then we can just visualize it at the end and plot the results as we did in the last video. So first of all here, we're just going to run through all the ground truth poses. Then we're going to calculate and estimate our pose. So first of all here, we're just going to run through all the images. Then we can go down and calculate our our trajectory. So our current pose will be our current pose multiplied with our transformation that we just got up here. So first of all, we're starting with one position. Then we're going to the next position. We're multiplying that with the new transformation that we estimated. So we just keep on incrementally estimating our pose and trajectory of our robot. And then we're just appending our estimated path and so on, visualize it here and the end as we're going to see after we've been through the code track, like implement visual odometry with stereo vision. But we can see here that we're just calling a function from visual odometry that just says get pose, and then we're just passing in the ith element, which is the frame, the index of the frame that we're passing in. So if we just go up to get pose, then we can actually see what is implemented inside this function. So first of all here, we're going to get the left image from the first image and also the second image. So we're both going to take the left image from the first frame and also the second frame. Then we're going to call a function here that is called get tile key points, because when we're using fast feature detector here, it acts like sometimes it just finds all the corners or like some fast features in the middle of the image, so we don't really spread it out. So we're going to divide our image into tile key points. So we're going to have tiles, which is 10 by 20. And then we're just going to pass in our image, divide it into tiles. So then we're doing fast detection in one tile, another tile, the next tile, and so on. So we actually like run through the whole image, get features from all the different kind of tiles, and then we're just combining those. So we just spread out all the features that we're detecting in our image. If we go up to the tile key points here, we can actually see how it's implemented. So here we can get the tile key points, the tile height, and also the tile width. Down here, we just have our get key points. So we have our X and the Y value. So first of all, we're just tiling, we're just getting the image tiles. So here we're actually just slicing our images with our X and Y here. So our get our key points would also just increment in value. So we can just take this the tiles here, or like we can slice the images with the tile height and also the tile width. Then we're going to detect the features in our tile. So we're just going to call fast features.detect, and then we just specify our tile here that we got, and then we will have the key points in a single tile in this example. Then we can have a for loop here, just correct the coordinate for that point. So basically here we're just going to run through all the points, because now we have a tile, we just took out that tile, then we want to correct that to our original image again. So all the coordinate dimensions, or like all the coordinates, is in the original image instead of only the tiles. Then we can get the 10 best key points here. So if we have more than 10 key points, we're just sorting them with our lambda function here. So basically we're just returning the best 10 key points that we found in that tile, and then we just have a number of tiles in our image that we can then combine later on. Then this function here, it just returns our key points, and then down here at the bottom we actually just have a function running through a for loop. So we actually just divide our image into a number of tiles, and then this get key points function, it actually just returns the key points, or the 10 best key points in that tile. And then at the end here, we have just appended all the key points from all the tiles into this key points list. And then we can basically just concatenate our key point list here and then return it at the end. So the resulting flattened list here would actually just be all the key points that were detected in all the tiles in our window, or like in our image. So this will be exactly the same as just doing like orb detection. So we just get our features and descriptors and so on. But this here is just to spread out our features a lot more in our image, because if you're just running this fast features detect on our image, sometimes everything is just like somewhere in the image. Like for example, if we have a car driving around, we want to take any features like in the sky or at the road or something like that. Sometimes it will just be in like one small basket somewhere in the image, and we don't really want that, so we're just spreading out the features more in our image. So then we can go down and see what is the next function that we call in this get pose function. So if we go down here, now we can actually track our key points. So now we have found the key points in the left image, then we're going to track the key points from the two left images. So we're going to pass in the frame 1 for the left image and frame 2 for the left image. So the idea here in the track points is actually like that we're tracking the points, and now we've detected the points. We've also generated the disparity map for the two images that we have. Then we can use the disparities together with the key points that we just found in the left images, and then we can actually map that so we can find the key points, the exact same key points in the right image by using the disparity map. And then we actually have both the key points in the left image, the right image. We can triangulate those and get really good 3D points out in the world, and then we can use that to estimate our pose and also estimate our trajectory and the path of our robot or car. So if we just go up to the track key points function and see what it does. So basically here we're just going up, calculate the right queue. So here we have our track key points. We get our first image, second image, and also the key points in the left image. We also specify maximum error, that when we're actually going to do some optimization and so on later on when we're going to solve these squares. So when our maximum error is good enough. So down here we can convert the key points into a vector of points, and then we can expand the dimensions so we can like select the good ones. So we want to find the good key points in our images, and then we want to use that because we're going to use optical flow to actually track our key points from one frame to the other. So basically here is just like how we can track our features from one frame to the other, because in binoculars, visual odometry, we track them with our descriptors. So when we're using orb, sift, or something like that, we also get some descriptors, and then we can use those descriptors with some matcher. We use the flan-based matcher in that video, and then we can use that to track the points in our image. But this way here, we're going to use optical flow. Again, I have also videos about optical flows here on the channel if you want to know more details about like what is optical flow, how it can be used, and we also have some really nice visualization of optical flow, both dense optical flow but also sparse optical flow. Then we're going to convert here a state vector boolean so we can use it as a mask. So basically here we just want to find all the features that we want to track in our image from optical flow. Then we can just set here that if we just set an under threshold here, so we use the mask to see where in our error do we actually want, like where is the error lower than our maximum error that we specified, and put in as an argument here to our function. And then we're going to select those key points and go with those key points later on. So basically here we're just setting up a we're setting up a mask where the error is lower than the maximum error that we specified. Then we can use that exact mask here on the threshold to get the correct key point that we actually want to use. So we want to take our track key points, and then we just go in and take the trackable key points and also the key point that is under this maximum error threshold that we set. Then we're going to just call around here, so we're just rounding out our track key points. And then basically here we just have all the good key points that we've now filtered with the error that we set up here at the top. So this is actually one parameter that you can play around with if you don't get good enough results, and so on. So basically here we can just remove the key points that is outside the image, because we don't want key points that is outside the image. We only want key points that we can see in both the left image and also the right image. So we can actually triangulate those and get the 3D points out in the world. Then we're going to return the track key points 1 and also the track key points 2, because those will be the key points in the left image and also in the first frame and the second frame. And then we can return those and get the right key points in the right images. So both the first frame and the second frame in the right image. We can also take another approach where we're detecting the key points. We can use orb in the left image and the right image. And then we can match those with the descriptors, and then we can triangulate those points. Instead of creating disparity maps, we can just use some sparse calculations with triangulation, and then we can also use that to do visual odometry. But here we can get a lot of features. We just create a disparity map. We're going to use a lot of those disparities to actually find the features in the right image. So this is also a really good result and a really good approach. And you can try out both. We're actually probably going to make another video where we're going to go with the other approach. But again, as you will see in the end of the video here, we're going to get some really nice results when we're doing visual odometry with a stereo camera. So now we're just returning those track key points. Then we can go down and calculate the right Qs. So here we're basically just passing in our Q1 and Q2, and then disparities for the first and the second image. But if we just go down here again to the estimate pose or get pose, then we can see when we have actually tracked our key points, we're just going to calculate the disparities. Again, we're just going to compute this function. So we're going into disparity.compute. We're passing in the left image and also the right images. And then we're just going to compute the disparity maps that we have seen in all the other videos throughout the channel and so on. So now we're calculating the disparities. And then from the disparities, we can actually calculate the right key points. So if you go into the calculate right key points here function that we just created up here. So then basically we're just going in, we get the indexes of our disparities. So basically we just pass in our feature points, we get the corresponding indexes of those disparities, and then we're just returning that. Then we can get the disparities for the feature points and also the mask for the minimum disparities and also the maximum disparities. So here we're just getting disparities, the first disparities and the second disparities. So this is one frame and the other frame. So this is only for the left camera. So here we can create a mask or two masks for both images. And then we can just combine the mask here by doing a logical AND. So basically this is just an operation that we're doing to combine the two masks that we created up here with the indexes of our disparity maps. Then we can get the feature point and disparity maps that were inbound. So we created this mask up here. So basically we can get the Q1s, the Q2s, and also disparity 1 and disparity 2, which is inbound in our image that we can then use later on. Then we're going to calculate the right feature points, and this is basically just that we're taking the Q points here. So we're just going to make a copy of the Q1s in the left image and the second frame, so the first frame and the second frame. And then we're actually just going to subtract the disparities that we got, because this one and this two is actually only the disparities for the feature point that we found in the left image. And then when we're subtracting the disparities that we found, we will actually get the corresponding X value in our right image, because we're taking the left image, then we want to find the exact same feature point in the right image, and then we can actually, because we have rectified images, we can just directly use the disparities, and then we're just subtracting disparities from our left image values, and then we get the right image values as we can see here. Then we're just returning everything. We're returning the key points in the first left frame, the second left frame, and also for the right frames in our image. Then we're going to create the last function here, which is actually just calculate the 3D points before we're estimating the pose. So here we can calculate the 3D points Basically here, we're just going up here, we're going to triangulate the points. We're just using the OpenCV function triangulate points. We pass in the projection matrix for the left camera and also the right camera, and then we just have the points from our feature points from a left image and the right image for the first frame. Then we're going to do this unhomogenization, so we just get the correct coordinates. We're going to do the same thing here for the second frame. So we both do triangulation from the first frame, the second frame, then we have 3D points from those frames, and then we can use that later on to actually estimate the pose. So this is just to calculate the 3D points in the real world of the different kind of features that we're detecting and tracking in the frames, like frame by frame in our stereo camera. So the last function here that we're calling is actually just our estimator pose, and this function here returns the transformation matrix, which is actually just the one that we're multiplying with our current pose, so we get our trajectory and the path of our robot or car that is moving around in the environment where we're estimating the pose by using visual odometry with a stereo camera. So the last function here that we're going to go through is the estimate pose before we're going to run the program, so you can see the really nice results that we get by using this stereo vision for visual odometry. So last function here, estimate pose, we pass in the Q1 values here, and also the 3D points. So this is the left and the right image key points, the 3D points for the left and the right image, or like the first frame and the second frame. And then also we're going to specify a maximum number of iterations because we're going to solve least squares. So this is basically just an optimization problem where we have a number of unknowns in a number of equations, and then we're basically just going to use least square to solve and optimize a system. So down here we can see that early termination threshold equals 5. We're only going to run a number of iterations here, 100. If you want your system to run faster, you can like lower this value here. If you want it to be more robust and more precise and do better optimization, you can look at it, you can like put in a higher value here. You can see the results, but it really depends on your system and what you want to do with your visual odometry. So here we just, first of all, our minimum value, we just set that to infinity and our early termination equal to 5. Then we're just going to have a for loop here running through the maximum number of iterations that we want to do when we're doing least squares optimization. We're going to choose 6 random feature points. So we're just going to take 6 random feature points from our feature points list. So this is basically just our Q1. So this is the feature points in our left image. Basically here, we're just going to take those indexes from all the samples that we have. So both in our Q1, the Q2s, and the 3D points as well. Then we're just taking 6 random points for all those lists that we have. So we're going to make an initial guess here. We just going to set our initial guess here equal to 0. And then we can just use SciPy to actually do our least squares optimization. So this is our reproject residual. So basically we're just going to minimize this reprojection residual or the reprojection error, because when we're taking our 3D points, we want to reproject that down to our image, and then we want to lower that reprojection error. So this is the function here that we're going to solve or like to optimize. We're going to pass in our initial guess and also the method that we're going to use. So some of these is actually just standard parameters. You can just use those. You can play around with them, look up the documentation on SciPy's website. You can try out some other different kind of like methods. But in this video here, we're going to use the least squares method. And also we're going to run this through a number of iterations, which is in this case 100. Then we can calculate the error here for optimized transformation. So this will be our optimized result. This is basically just our reprojection residual. So we're going to take the X value here of our optimal result. So this will actually just be the result that we're returning when we're doing this least squares optimization. Then we pass in our feature points and also our 3D points because we want to reproject our residuals. And then basically here we're just calculating an error here by using the norm, and then we're just summing up the norm. So this is basically just a metric for calculating the error when we're looking at these residuals. Then we're going to check if the error is less than the current minimum error, and then we save the results if it is. If it's not, we're going to increment our early termination, and if our termination here just becomes greater than our early termination threshold or equal to, we're just going to break because we haven't found any better results by running like 5 iterations. So after 5 iterations, if we haven't found a better solution, we'll just terminate this optimization process here that we're doing. So here our error will just be equal to our minimum error, and our output pose here would actually be equal to our optimized result.x. So this will be the results of our least squares optimization. That will be our output pose that we can then output here at the end, or return from this function. So this output pose here is act like our transformation or our estimated pose, because we're doing least squares and optimizing this reprojection residual. So here, our output pose, we're going to take the rotation vector. So basically here, we just take the first 3 values in our output pose. We're going to use Residuals here to convert our rotation vector to a rotation matrix. And then we can get the translation vector, which is actually like just the 3 next points that we have, or like the 3 last points in our output pose. That will be our transformation. Then we use the transform function that were implemented in the start. So we're going to pass in the rotation and the translation, and they will basically just return a transformation matrix that we can then use to multiply with our current pose, and then we can estimate the path and the trajectory of our robot. So we're going to return that. We have now everything. This is the function that we call here. We have our tile key points here, like we have our key points here in the first frame and the second frame for our left image. Then we're estimating the pose, calculating the right cues here, and so on, and also the 3D points. Then we're minimizing our reprojection error, and then we're estimating the pose based on least squares and also the lowest residual error. We will get the transformation matrix, and then we're going to return it. So this transformation matrix is the one that we're returning here when we call vo.getPose of the ith element, which is the index of our frames that we're running through. Then we're multiplying our current pose with a transformation and just estimating trajectory and the path that we're actually like doing, or like driving with our robot or a car in this example. So now we've been through the whole code here. I'm just going to run the program so we can see what is going on. First of all, we're just going to go with the sequence 1, and we're going to also play the trip here so we can see all the frames that we're running through. We're also going to see the features that we're detecting in the frames. So here we can see that we're just driving. We have 51 frames. So this is basically just our trip that we're running through. Now we can see that we're estimating all the poses. We get around like 6 poses estimated per second. And when the program here is done, it will open up an HTML file and show the results. So over here to the left, we can see the path that we're estimating. So it's actually really nice. We get the ground truth in blue and also predictions in green. And then over here to the right, we can see the error. So when we're doing visual odometry with no global optimization or SLAM, we can just see we have this accumulated error, because when we actually get an error, it would just keep accumulating up and up and up until we actually close our loop, and then we can do optimization, refine our pose back again. So here we're just going to zoom in to see some of the results, so we can see we actually track it really nicely. These are in actual meter units, so we can see here that we're driving around like 60 meters, and down here we can see how far are we from the ground truth when we're driving around in this car. So here we're around maybe like 1 meter away, so we're estimating we have an error of 1 meter here at the end of our program. But we can see here, we start here really nice, we're estimating the pose, we get some error here, we get some fluctuations a bit, we get a big error here, and it's just accumulating up and up. We can try to optimize it by tuning some of the parameters and so on, but also if we're doing loop detection and so on, we can optimize it way more. So this is actually like really nice result by just running this script. Again, everything will be on my GitHub, and also from the last video, everything else on my GitHub. You just go in there, download the repository, run this code here for yourself, play around the parameters. You basically just have to clone the directory and then run the Python file that I just showed you here in the last couple of minutes, and then you can just run it and you can see the results here by yourself. So now we can go in and actually run the second sequence. So basically everything we have to do is just run KITTI sequence _2, and then we can just go up, run our program again. So basically we're just running through our trip here again. If we hit escape, it will stop it, but now we can just see the frames that we have. So now we have a nice curve here in our sequence, and we want to estimate the pose or trajectory of that like structure that we're doing. So now we can see we get around 5 poses per minute, maybe because we're detecting more key points. But here we can see we get this really nice curve around here with the ground truth. Our prediction is also really good, but we can see that the error here, it just keeps accumulating. We just like it's actually just accumulating linearly here, the number of frames that we get. So the more frames we get in, the greater our error will be, or like because our error here is just accumulating, as we can see. But again, we're still estimating this really nice curve here, or like this bend here. But again, we should be down here, but we're up here. And we can see here at the start, we track it really nice, but the further we come around here in the curve, like the more we kind of lose track of a robot or car that is driving around in the environment. So this is just really nice. It can be used for a lot of different kind of things. Again, you can play around with the parameters yourself, try to get some better results, just to make sure that you comment if you get some better results, or if you have some really nice ideas that we can try out to get a better optimization or like a better path estimated. In this example here, we can try out some other different kind of sequences and so on as well. But thank you guys for watching this video here, and remember the subscribe button and bell notification under the video, and also like this video here if you like the content and you want more in the future. It just really helped me and the YouTube channel out in a massive way. I'm currently also doing this deep learning tutorial where we're talking about like neural networks, how we can construct neural networks from scratch, the basic theory behind neural networks. We also have computer vision tutorials and so on, where we're talking about basic ML operations, camera calibration. Now we're combining it with some more real life applications and projects. So if you're interested in one of those tutorials, I'll link to one of them up here, or else I'll just see you next video, guys. Bye for now.